Section 2.1, Properties of Sets. In this section, we're going to start talking about sets. For example, this is a set of numbers 1, 2, 3, and the set is called set A. There's some definitions I would like to start with here. In our section 2.1 notes, it says that a set is any group or collection of objects. It doesn't have to be numbers. Could be letters, could be people, could be names of cars, it could be cities, it could be anything really. Just any group or collection of objects. Elements are the objects in a set. So for example, 1, 2, and 3 would be the elements that make up set A. We can list a set in a couple of different ways. We can use what's called the roster method, where we list the elements of a set inside a pair of braces. These are not parentheses, these are like squiggly things. They're called braces. So when I'm listing set A and set B and set C here, I'm using what's called the roster method. I'm literally just telling you what elements make up that set by putting the elements inside of these braces. Sometimes we use something called a word description where we verbally describe a set. We'll see that pop up in a little bit also. There are a few different basic number sets. The first three I would like to highlight. Natural numbers. When we say natural numbers, that's the same thing as what you might say as counting numbers. It's just the numbers you count with, the numbers you learned how to count with when you were a little kid. 1, 2, 3, 4, 5, 6, 7, 8, and so on. Those are called the natural numbers. Sometimes we use this letter N to represent the natural numbers, but this is the set of natural numbers right here. When we talk about the set of whole numbers, we include 0. It almost looks the same as the natural numbers, but it includes 0. So when we talk about the set of whole numbers, sometimes we use this W here, but when we talk about the set of whole numbers, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. When we talk about the set of integers, sometimes I'll use this notation for integers, this letter I, but when we talk about the set of integers, well, it's includes all of the whole numbers that we just mentioned, but now it includes all of the negatives of those also. So it goes forever in both directions here, set of integers. I'm not really going to highlight these next three very much at the moment. I just wanted to highlight those first three. But rational numbers, irrational numbers, and real numbers are other sort of popular basic number sets. But I do definitely want us to be aware of these first three for now. Some more definitions and things like that that are going to pop up. Sometimes we call something the empty set, and that just means a set is literally empty. It just has no elements in it, contains no elements. We can denote the empty set in two different ways. This symbol right here, which sort of looks like a 0 with a slash through it, that's one way to denote the empty set. Here's another way to denote the empty set. It's you draw those braces like we mentioned, but you just don't put anything in it. You literally leave it empty. Here's a symbol right here. This looks sort of like the letter E. It's not the letter E, but it kind of looks like it. This symbol is read, is an element of. To state, for example, that 4 is an element of the natural numbers, we can write this right here. 4 is an element of the natural numbers. 4 is an element of the natural numbers. We will do an example later, and we'll probably come back to this definition, but for now, let me just say a well-defined set is a set such that it is possible to determine whether any given item is an element of the set or not. If the description of the set has anything to do with someone's opinion, then it is not a well-defined set. We'll come back to that in a little bit, but basically, if it's based on fact, then it's well-defined. If the description of the set is based on fact, then it is a well-defined set. But if the description of the set involves your opinion on anything, it is not a well-defined set. We will also in a little bit do an example using the cardinality of a set. When we talk about the cardinality of a set, we're just talking about the number of elements in the set. So the cardinality of set A is just the number of elements in set A. And we sometimes denote it like this. You see that N with the A right there. We read that as number of elements in set A. Number of elements in set A. And then finally, before we get to our examples, I want to highlight the definitions of equal sets versus equivalent sets. When we say two sets are equal, we use this notation, the equal sign. When we say two sets are equivalent, we use this notation, like a tilde right there. They're not the same definition. When we're saying two sets are equal if and only if they have exactly the same elements. Like they literally have to be equal to each other. It's probably exactly what you think this definition means. Exactly the same. Now, if two sets are not exactly the same, but they do have the same number of elements, we can call those two sets equivalent. So this says A is equivalent to B if and only if A and B have the same number of elements. Those elements don't necessarily have to be the same things. It just has to be the same amount of elements in each set. So if we have the same amount of elements in each set, we can say those two sets are equivalent. The same thing as saying the number of elements in set A is equal to the number of elements in set B. The cardinality of set A equals the cardinality of set B. So if we have two sets where they have the same number of elements in them, we can say that A is equivalent to B. If they have the same number of elements in them, but those elements are also exactly the same things, we can say something even stronger. We can say A is equal to B. So those are the definitions I wanted to highlight before we get started with our examples here. So I would say this first one's not necessarily an example. It's just let's look at these three sets and let's just kind of talk about them based off of some of the definitions we just discussed. The last definition was equals versus equivalent. Notice that sets A and B have the same number of elements in them. They both have 1, 2, 3, 1, 2, 3. They both have three things inside of them, right? But those elements are not exactly the same thing, right? This is 1, 2, 3. This is 4, 5, 6. Although the cardinality of A and B is the same. But look at A and C. They do have exactly the same. I mean, they're literally equal to each other. So I could say, for example, that set A is equal to set C. That is a true statement. I cannot say set A is equal to set B, but since they have the same number of elements, they both have three elements, I can say that. I can say that A is equivalent to B. So just be careful of that equal to versus equivalent to. It is also true that A is equivalent to C, but we can say something even stronger since they're exactly the same. We can say A is equal to C. Again, this is just another way of saying that the number of elements in set A is equal to the number of elements in set B. These two statements are pretty much the same. They're pretty much telling us the same information. In fact, they both have three elements inside of them, right? This has three elements inside of them. This also has three elements inside of them. They don't happen to be the same exact elements, but they happen to each have three elements inside of them. Another thing I could say using some of the definitions is, for example, the number 2 is an element of set A. So you remember this notation right here? The number 2 is an element of set A. So that's a true statement. I could say that the number 6 is an element of set B because 6 lies inside of set B. Is 4 an element of C? No, that is not true, but we could do that. And when we do that, this is now true because we are saying 4 is not an element of set C. 4 is not there. 4 is not inside of set C. Okay, so these are just some things I wanted to do just to kind of get us used to some of those definitions that we saw. But let's go ahead and move on to some actual examples. First example says, use the roster method to write each of the given sets. So remember, the roster method is where we write those braces like that, and then we just list the elements of that set. So the first question says, let's use the roster method to write the set of whole numbers less than 4. Set of whole numbers less than 4. So let's think about that. Remember the definition of whole numbers. Definition of whole numbers was, well, it includes 0, and then it includes 1, 2, 3, 4, 5, and so on. It includes all the numbers that we count with, but it also includes 0. So if we're talking about the set of whole numbers less than 4, we're probably talking about these first few here that are less than 4, right? If we're talking about the set of whole numbers less than 4, we must be talking about 0, 1, 2, and 3. So here's what we call a word description of a set, and this is the roster method description, or the roster method way to write a set. So we can write a set using a word description, or we can write a set using the roster method. Of course, it's the same thing. Those are just two different ways to describe the same thing. Part B says, let's use the roster method to write the set of months that end with the letter Y. As a reminder, as I'm going through these problems, I would say pretty much every example that we do, my advice to you is to pause at some point early on in the page, and I would like you to try to do these problems on your own, and then come back and unpause the video and watch and see how you did. It's my suggestion. I'm just going to go through these problems. I'm advising you to pause and try to do the problems before you unpause and watch me continue with them. So part B says the set of months that end with the letter Y. We know the months of the year. January happens to end with the letter Y. February happens to end with the letter Y. Let's see, what do we have? March, April, May. May happens to end with the letter Y. June, July, August, September, October, November, December. I think that might be it, right? I think we have 4 months that end with the letter Y when we spell it out. And so this is a word description of that set. This is the roster method description or way to write that set. Part C says the set of states that border California. So if I asked you, for example, the set of states that border California, or the set of states that border Montana, or the set of states that border Tennessee, those types of questions, I would not ask you a question like that on a test because I don't expect you to know necessarily the set of states that border Montana, for example. So don't worry, I would not ask a question like this on a test, but I would possibly ask it on a lab because during lab you can go use your resources, right? You can go look up Google and, research things, right? So there's certain questions that we're going to see that I would say are not fair test questions, but they are definitely fair lab questions. I think these first two are good, fair test questions. I think this one is not something I would ask you on a test. But I mean, I'm assuming some of you know this answer anyways. Um, if not, well, Oregon touches California on the map, Nevada touches California on the map, and Arizona touches California on the map. So that's something you could go research though if this popped up as a lab question. I would not ask that as a test question. I do not think this is a fair test question. Let's continue to our next example. In the next example, I'm going to basically reverse this example. So in this example, we started with a word description and we wrote the roster method. But what if I gave you the roster method and asked you for the word description? So let's kind of reverse the process here. That's what we're about to see in the next example. So this is to write a word description of each set. Now for these types of questions, there might be more than one correct answer. If you look at part A here, the set is given to us using the roster method as containing the elements 2, 4, 6, 8. There may be more than one way to correctly write a word description of the set. So if you're working on these problems in your lab and you go check your answer, and the answer that I gave is a little bit different than yours, that you might still be okay. Again, my advice is you pause right now and you try these problems and then you unpause. I'll tell you what I wrote down for part A. Now, first of all, some people might just say, I get some people say, well, I think those are even numbers. And they just write that down as their answer, even numbers. Okay, well, I agree those are even numbers, but if I asked you to write out the even numbers, you would write out a lot more numbers than just those. You would write out 2, 4, 6, 8, probably 10, 12, 14, 16. If you just try to describe a set just by saying even numbers, it's way more than just this. So that's not a good word description. That's not a very precise word description. We have to say something about how it stops at 8, like it doesn't include 10, 12, 14, 16, and so on. And also the other way, like 0 is actually an even number also, but 0 is not included. And to be real precise, -2 and -4 and -6, they are also even numbers. So we need to somehow, we might use the word even numbers, but we need to be more precise. So I wrote it as the set of even. Now, some people might say the set of even numbers less than 10. But we got to be careful because again, that would include 0 and that would include -2 and -4 and -6 because to make a number even, it just has to be divisible by 2. So negative numbers are even sometimes if they're divisible by 2. So I need to somehow say something where I'm not going to have negative numbers involved. I'm not going to have zero involved. If you remember the definition of natural numbers, that didn't involve zero. That didn't involve the negatives. That just involved one, two, three, four, five, six, and so on. So if I said this is the set of even natural numbers, we're close to a good word description right now, right? The set of even natural numbers. That would include 2, 4, 6, 8, but that would also still include 10, 12, 14, 16, and so on. So let me say the set of even natural numbers that are less than 10. Now I think we have a good word description of that set. The set of even natural numbers less than 10. Are there other correct answers? Yes. For these types of problems, there could be more than one correct answer. So you may have written down something a little bit different, but as long as whatever you wrote down precisely describes only those four things, then you are good. Part B, 5, 10, 15, 20, 25, 30, 35, 40. What do they all have in common? They look like they're multiples of 5, right? But I can't just say multiples of 5. Um, that would not be a good answer. Multiples of 5. Multiples of 5 would include 45 and 50 and 55 and 60. Multiples of 5 would actually also include technically 0 and negative 1. I'm sorry. Let's be careful. I want to be careful of how I'm saying that. Um, even numbers do definitely go the other way and include 0 and negative 2 and negative 4. When we say multiples of 5, we actually mean 5 times 1, 5 times 2, 5 times 3. So I wouldn't want to say multiples of 5 include 0 or the negatives. So, but multiples of 5 is still not a good answer because it would include 45 and 50 and 55 and 60. We need to somehow say how it stops here, right? And so it might have to do with something like that, but that's not a good final answer. What I ended up writing down was the set of positive multiples of 5 less than 40. That's definitely a good answer. Is that the only correct answer? No, we probably could have had some other way to write it. I probably could argue that I don't even need the word positive in there, but it doesn't hurt. Again, when we say multiples of 5, we usually mean 5 times 1, 5 times 2, 5 times 3. So the word positive maybe wasn't necessary, but again, it doesn't hurt. Doesn't make the answer wrong. A set of positive multiples of 5 less than 45 is one correct way to describe this. Okay, the next problem says penny, nickel, dime. Sometimes I'll see students just write that and then they move on with their life like everything is fine. It's not a good answer. There are other types of coins out there besides penny, nickels, and dimes. First of all, there are other countries that have their own coins, but in I don't see quarters here, but that's a coin, right? So we got to be more precise, right? Coins is not a good answer on its own. Here's one good answer, the set of US coins worth less than 25 cents. Is that the only good answer? No, that's one good answer. You may have come up with a different correct answer. Again, for these types of problems, there could be more than one correct answer. The last one, I don't think the last one is a fair test question. I think the first three, these are good test questions. I would not ask you this one on a test, but some of you might know that these are LeBron James's kid, right? basketball player. LeBron James, he has 3 kids, and those are their names. Maybe that would be a lab question. That would not be a very fair test question for me to ask you. But that is a word description of this set, Bronny, Bryce, and Zuri. Okay, moving on to the next example. The next example says, let's try to determine whether each set is well defined or not. Determine whether each set is well defined or not. Let's remind ourselves what the word well defined means. I had highlighted that definition right here. A well-defined set is a set such that it is possible to determine whether any given item is an element of the set or not. If the description of the set has anything to do with someone's opinion, then it is not a well-defined set. So if it has to do only with facts, it is well defined. If it has anything to do with opinion, it is not well defined. Let me kind of write that down over here. If it has anything to do with facts, the description of the set has only to do with facts, it is well defined. If the description of the set has to do with someone's opinion, it is not well defined. It is not a well defined set. So take a minute and pause this and try to see what you think about these 4 questions. The set of good pizza places in Elk Grove, the set of tall buildings in Sacramento, the set of former Colorado senators born in the 1800s, and finally the set of the 5 U.S. states with the most land area in square miles. Go ahead and pause. Try to write down whether you think these are well-defined sets or not. And then unpause and we will go through them together. So the set of good pizza places in Elk Grove. You may be able to list some of these. You may like certain pizza places in Elk Grove. So you're like, I can do this. I can write down my 3 favorite pizza places in Elk Grove. This must be a well-defined set because I know how to write it down. But the problem is whatever you write down might be different than whatever someone else writes down. And that's because they might like pizza place that you don't, or vice versa. This question has to do with your opinion. This is not a factual question. It's an opinion type question. This is not a well-defined set. It's not a well-defined set because different people might have different answers. What you think of as a good pizza place in Elk Grove, somebody else might not, and vice versa. Not a well-defined set because it has to do with your opinion. It's not a factual question. It has to do with your opinion. Same actually with part B. Part B is not a well-defined set. The set of tall buildings in Sacramento. Well, what does that mean? Like, I might look at a building and say, hey, that's a tall building. But you might look at the same building and say, oh, it's not tall enough for me to call it tall. It has to be taller for me to call it tall. What does the word tall mean? It means something different to everyone. What does the word good mean? You might think something's good. I might think it's not good. It has to do with our opinion. It is not well defined. I might have my answer for what I think are the set of tall buildings in Sacramento. You might have your own answer for what you think of as the set of tall buildings in Sacramento, because our definition of tall might be different, right? It's not precise enough. What's the definition of tall? Now, if it said the set of buildings in Sacramento that are more than 100 feet high, that's a different question. That would be well defined because then it's very precise and it's based on fact and it's not based on your opinion. So these first two are not well defined, and basically because the word good and the word tall, they what do they mean exactly? They might mean different things to different people. I might think something's good, you might think it's not good. I might call something tall, you might say, no, I don't think that's tall. Not tall enough for me to call it tall, right? Part C is well defined. Part C is well defined. The set of former Colorado senators who were born in the 1800s. Now, what I sometimes hear my students say is, well, I don't think that's well defined because I can't write any down. I don't know what they are. I know what I know some good pizza places in Elk Grove. I can write what I think the set is. So some people think this is well defined because they can write some down, and some people think this is not well defined because they can't. Again, it's not whether you can or can't write anything down. It's does it have to do with fact or opinion? There's no opinion in this one. There's no opinion involved in part C. The set of former Colorado senators born in the 1800s, people either are on this list or they're not. They're either in this set or they're not. Doesn't matter what you think about it. Doesn't matter what your opinion is. Even though I bet you probably no one watching this video can name even one Colorado senator who was born in the 1800s. I can't. But if we did our research and we looked it up, we would all have the same answers because it has nothing to do with your opinion. It's just fact. There are some Colorado senators who were born in the 1800s. If we figured out who they were and wrote them out in a set form, that would be the answer, and we'd all have the same answer, and there's no arguing it, right? It has nothing to do with your opinion. And also the same for part D. Part D is well defined because it just has to do with fact. Doesn't matter what your opinion is on this. Doesn't matter what you think are the five U.S. states with the most land area. It's what are the five U.S. states with the most land area. Even though you might not even know what they are. You probably know a couple of them, I'm guessing, because you know some of the big states, but you may not be able to come up with all five of these, but it's still a well-defined set because it's not based on your opinion. It's just based on fact. What are the five states in the United States that are the biggest as far as land area goes? That's a factual thing. That is a well-defined set. We would, if we did it correctly, we would all have the same answer in the same five states in the set if we did our research, right? Just if you're interested, I'm going to tell you in order what they are. Alaska is actually the biggest state in land area. Texas is the second biggest state. And Texas is really big, but Alaska is more than twice the size of Texas. So Texas isn't very big compared to Alaska. California is next. Montana, and then finally New Mexico. So this is actually the set that we are talking about. And there's no arguing that. There's no arguing that. It's just facts. You can't say, well, I like Arizona, so I think Arizona should be on this list. My opinion is I feel like Arizona should be on this list. Well, it doesn't matter. Math doesn't care how you feel. Math's not interested in how you feel. Math's not interested in your feelings. Math is interested in facts, right? And so it doesn't matter if your opinion is that Arizona should be on this list because it's not one of 5 U.S. states with the most land area in square miles. It doesn't matter that you say, well, my truth is that Arizona should be on this list, so I'm going to put it on there and you need to be okay with that. It's not how math works. Math doesn't care about your feelings. Math cares about facts. Okay, moving on to the next question. Find the cardinality of each of the given sets. Find the cardinality of each of the given sets. Let's go remind ourselves what the word cardinality means. That was something that we saw in the beginning. Right here, cardinality. The cardinality of set A simply means the number of elements in set A. And it's denoted by this notation in with the A right there. That means number of elements in set A. That's called the cardinality of set A. So when we're asked to find the cardinality of set A, I'm not necessarily asking you what does set A look like, although you could go figure that out if you wanted to. I'm just asking you how many elements are in that set. It wouldn't be a bad idea to go figure out what set A looks like, but that's not what I'm asking you. Your answer to this type of question, when we're talking about cardinality, should be something like this. The number of elements in set A equals what? Does it equal to 1 or 2 or 5 or 10? How many NFL teams are in Florida? That's what I need to put there. Okay, so when the question talks about cardinality, your answer is a number like 1 or 2 or 3 or 4 or 5 or something like that. I'm not asking you to write out the set. You might still write it out just so you can get this, but your answer is a number that I'm going to put right there. This is not a fair test question. I would not ask you this on a test. I could ask you a question like this on a lab because you can go research, you can go use Google, you can phone a friend, you can do whatever on the lab. Not a fair test question, though. Don't stress out about that. I'm going to tell you the answer is 3. Those teams are the Jacksonville Jaguars, the Miami Dolphins, and the Tampa Bay Buccaneers. So again, it's not a bad idea to write this down, but that's not my answer. My answer is 1, 2, 3, 3, 1, 2, 3. My answer is 3 because the cardinality is not necessarily asking you for the set. It's asking you how many elements are in that set. Part B is not a fair test question either. But my answer to this question is going to be a number. I'm not asking you to list all the cities in Hawaii that have a population over 500,000. I'm asking you how many cities in Hawaii have a population over 500,000. That's what I'm asking you. Not a fair test question. Good lab question. On the test, I don't let you use Google, right? On the test, I don't let you ask your friend. On the test, I don't let you call Hawaii and find out how many cities have a population over 500,000. But on a lab, you can do whatever you want. So if you went to research the biggest cities in Hawaii and checked how many of them have a population over 500,000, you will actually discover that none of them do. In fact, Honolulu has a population somewhere around 350,000, but that's the biggest city in Hawaii. And there are no cities in Hawaii with a population over 500,000. This is our first example today of what we would call the empty set. The empty set is literally empty. It's the set with nothing in it. It's empty. Just like this is a set with those three elements in it. This is a set with nothing inside of it. It's an empty set. The empty set has 0 elements inside of it. You can write the empty set in 2 different ways. You can write it like that, or you can write it like that. That is not the number 0. The number of 0 describes how many things are inside the empty set. That is not the number 0. It looks like a 0 with a slash through it, but that is not the same as the number 0. That is not a number at all. That's a different way to describe the empty set. Those 2 things mean the same thing. Those are just 2 different types of notation that means the same thing. Sometimes I see people do this. I think they just get excited and carried away and they're like, oh, I'm just going to do both of them like that. That doesn't make any sense at all. I don't know what you're talking about when you write that. This is the empty set inside of an empty set. You can't have a set inside of a set. That really doesn't make sense. The empty set has 0 elements in it. So the number of elements in set B would be 0. The number of elements in set C, this is also not a fair test question. Don't worry, I would not ask you this on a test. I don't expect everyone to be an expert on the Mexican flag. The answer is 3, by the way. Green, white, and red. If you go look at the Mexican flag, you'll see the background colors are green, white, and red. These primary colors in the background is what we were referring to there, green, white, and red. So there's 3 of them, right? Now, 3 is my answer. Green, white, and red is not my answer, actually. This is not my answer. 3 is my answer. When you're talking about the cardinality, your answer should be a number. It's just helpful sometimes to write this out so you know how many there are. 1, 2, 3, 1, 2, 3, 0. Okay. Next question, cardinality of set D is a number. Don't freak out. This is probably the easiest question of the day. How many elements does set D have? 1, 2, 3, 4, 5. We're done. Set D has 5 elements. The cardinality of set D is 5. 1, 2, 3, 4, 5. Not a difficult question. Don't make that difficult. Now, these last 3 problems, we're going to turn the page to another one. We're still talking about cardinality. I'm still asking you to find the cardinality of these sets. So we're still doing the same example. We're going to continue to a different page. But these last 3 problems are a little more difficult than what we just saw here, for example, in part D. Again, as a reminder, we are still talking about the cardinality of these sets. That means the number of elements inside of the set. How many elements does the set have? Okay. So for these are the last 3 things we're going to do in this section. But just as a reminder, we are being asked to find the cardinality of the set. Set E consists of 2, 4, 6, 8, 10. And you see dot, 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 and you see 60. What we mean by that dot, dot, dot is we mean a pattern has been established here. Let's let that pattern continue and stop when we hit 60. So this set consists of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, all the way up, and we stop at 60. That's what the dot, dot, dot means. It means continue that pattern. Obviously, our pattern is we're adding 2 each time. 12, 14, 16, and so on, stopping at 60. How many elements are in that set? And same thing here. We started a pattern, 7, 14, 21. We're adding 7 each time. Plus 7, plus 7, plus 7, plus 7. Keep doing that. So 42, 49, 56, all the way up to 644. And then this last one's the most difficult. 11, 17, 23, 29. There is a pattern. We're adding 6 each time, if you notice that. 11 plus 6 is 17. 17 plus 6 is 23. 23 plus 6 is 29. So 41 plus 6 would be 47, and then 53, and then 59, all the way up, and then we stop at 941. It's a tough one. Try to pause the video and try to go do these 3 problems. Remember, your answer is a number. Your answer is going to look like this. The number of elements in set E equals what? The number of elements in set F equals what? The number of elements in set G equals what? That's what we mean by cardinality. Your answer is going to be a number. Are there 5 elements? Are there 50 elements? Are there 100 elements? Are there 80 elements? How many elements are inside each set? Go ahead and try these and then unpause and come back and we can talk about them. Now, I think most of you probably got 30 for this one. Most of you say, well, these are multiples of 2. That's 2 times 30. Yeah. 2 times 1, 2 times 2, 2 times 3, 2 times 4, 2 times 5. That's 2 times 30. I mean, it is true that 60 divided by 2 is 30. Yeah. I would say the same thing for part F. These are multiples of 7, right? 7 times 1, 7 times 2, 7 times 3, 7 times 4, 7 times 5, all the way up to, this is probably some other multiple of 7. So go ahead and do 644 divided by 7. If you do 644 divided by 7, you will see that 92 is the answer. This must be 7 times 92. So 7 times 1, 7 times 2, 7 times 3, all the way up to 7 times 92. There must be 92 elements in that set. So if it's as straightforward as that, like these are just all the multiples of 2, these are all the multiples of 7, just take the last number and divide by the first number and you're done. But it's not always that easy. The last question is not that easy. Because we started at 11, but these are not multiples of 11. We started at 11, but we went up by 6, right? Here we started at 2 and we went up by 2. That's easy. Here we started at 7 and we went up by 7. So that's easy. Here I started at 11, but I didn't go up by 11. I went up by 6. This is a more difficult question. Let's talk about how we could do this last one. I'm going to teach you a little trick for this last one. Okay. Try to bear with me here. What I'm going to do is I'm going to take the last minus the first, the last number minus the first number. And then I'm going to take that answer and I'm going to divide it by, in this case, I'm going to divide it by 6. Why am I dividing by 6? Because we are adding 6 every time, right? That's what the pattern is I'm adding 6 every time. I'm adding 6 to get from 17 to 23. and I'm adding 6 to get from 23 to 29. We take 930 divided by 6, we get 155. That is not my final answer, actually. This is super weird, and we'll kind of try to understand why we're doing this last step. But what you always have to do at the end here is add 1, and then you have your final answer. Let's try to understand these steps. What if I tried to apply the same logic up here? I know that we know that 60 divided by 2 is 30 and so on. But what if we didn't use that logic? What if I tried to use this logic? What if I took 60 minus 2, which would be 58? And then what if I divided 58 by 2? Why would I be dividing by 2? Because that's the pattern. I'm going up by 2's on this one. 58 divided by 2 would be 29. 29 is not my final answer. We know the final answer is 30. If you use this logic, you always have to add 1 at the end. That's how you get your final answer. That's weird. Why do we have to add 1 at the end? What's going on with that? Let's keep talking about that. I mean, it looks like the pattern, it looks like what I'm doing here is I'm taking the last number minus the first number. I'm subtracting them, I'm getting an answer, and then I'm dividing by whatever the pattern is going up by. In this case, the pattern is going up by 6's. We're adding 6 every time. And then you just always have to add 1 at the end. That's really it. For some of you, you're like, I got it because that's what my teacher said. If my teacher said that's the rule, that's the rule, and okay, I'm good with it. Others of you are like, I want to know why. My teacher said that's the rule, but why is that the rule? Why does that work? Why do we have to add 1 at the end? So let's continue talking a little bit here. We're almost finished, but we took the last number minus the first number. We took that answer and divided by whatever the pattern was. In this case, the pattern is we are going up by 2's. But we always have to add 1 at the end of that to get the correct answer of, in this case, 30, in this case, 156. I don't think if I were you, I would not do this for this question because if it starts with the same number that it's going up by, it is much easier. You just take the last number divided by the first number and you're done. Let me say that again. If the pattern that we are going up by, you know how we're adding 7? We're adding 7 and it also started at 7. If those two numbers are the same, just take the last divided by the first and you're done. Okay. If those two numbers are the same, just take the last divided by the first and then you're done. But what if those two numbers are not the same? What if we start at 11, but we don't go up by 11? Those two numbers are not the same. When those two numbers are not the same, I suggest you use this trick that we did down here. The trick would work, if you wanted to, you could go 644 minus 7, which is 637. And then you could take 637 divided by whatever the numbers are jumping up by. In this case, they're jumping up by 7's, right? 637 divided by 7 is 91. But 91 is not our answer because we know 92 is our answer. So you always have to add 1 at the end right there. Again, you could take the last. This is true whenever they're going up by a certain amount of number, like a certain number every time, right? This is going up by 7 every time. This is going up by 6 every time. This is going up by 2 every time. Whenever they're going up by a certain number each time, you can always take the last minus the first. You can take that answer and divide by whatever that pattern is, whatever they are going up by. But don't forget to always add 1 at the very end. Again, I think you should only do that little trick for the last one because that trick is not really necessary on the first two. Because on the first two, the number they are jumping up by is the same as the number we started with. The number we are jumping up by is the same as the number we started with. It's much easier in that case. In that case, we just took last divided by first. And that was a much quicker way to get to the right answer. Last divided by first. It's a much quicker way to get the correct answer. But that's not going to work if the number that we start with is not the same as the number that we are jumping up by. Then we kind of need to do something like this. Why are we adding 1 at the end? That's a little weird. I mean, first of all, just get you the right answer. You can see why we need to do it because of the first two. But let's say, for example, you were in a history class and your teacher asked you to go read pages 15 through 20 tonight. And then you're going to come back and talk about pages 15 through 20 the next day. So your history teacher says, go home and read pages 15 through 20 in your textbook. We're going to have a discussion on that tomorrow. How many pages are we actually reading? Some people think we're reading 5 pages because they would do 20 minus 5. I'm sorry, they would do 20 minus 15. I think a lot of people would say we have to go home and read 5 pages tonight because 20 minus 15 is 5. But that's not the right answer. I agree 20 minus 15 is 5. But you're actually reading 6 pages. Because if you're reading these pages, you have to go home and read page 15, and you have to go home and read page 16 and 17 and 18 and 19 and 20. That's not 5 things. That's 1, 2, 3, 4, 5, 6 things. So just doing 20 minus 15, that actually doesn't get you the right answer. A lot of people think it does. I bet you 90% of the people that you ask this question to would tell you you're about to go home and read 5 pages, but they're wrong. It's 6 pages. And so that's a partial reason for why we always have to add. Like, I hope that it kind of helps you understand why we always have to add 1 at the end. That wraps up this particular section. Thank you for watching.